Hi, hello guys. This is our last video of nuclear physics for year 11 physics course. Okay, in our previous videos we've discussed the nature of nuclear transmutations. Okay, so here's the curriculum. All right. So we know that nuclear transmutation, there are several types. Okay, so what do we mean by nuclear transmutation? If you still remember the definition, that means new elements have been formed when there are nuclear reactions. Okay, so we've learned two types. One is what we call the natural transmutation. The other is artificial. Okay, so for natural one, we've learned mainly the radioactive decay. Radioactive decays. Okay, so there are three types of decay: alpha, beta, and gamma. All right. So for radioactive decay, energy is released. Okay, and also there are some small particles. But when we discuss the scale of the transmutation, radioactive decay is just a small scale of transmutation, because normally there will be a slight change in the number of nucleons or the number of protons or neutrons. Okay. So that means you might have different types of radioactive decays, but normally all these decays, they release energy, but not too much energy. So today we are going to learn two types of artificial nuclear transmutations. They are what we call fission and fusion. Okay, right? So both fission and fusion on the Earth, they can't happen naturally. You must have some artificial intervention, right, by our technology to make it happen. But once they happen, they release huge amounts of energy. Okay, so when you compare with radioactive decay, fission or fusion, they release greater energy. Okay, and radioactive decay, they release less energy. Okay, but all this energy, no matter whether it's less or more, both came from what we understand: mass defect. Okay, all this energy released from the nuclear reactions, okay, that must follow, is followed by the mass defect. Okay, and from the mass defect to the energy release, we have Einstein's mass energy equivalence, if you still remember that. Okay, so that's Einstein's mass energy equivalence. We're going to use this formula. Okay, all right, so that's how we relate that mass defect to the energy release. And for all these reactions, remember that after the reactions, the reactants should become more stable than the products should become more stable than the reactants, or you might say the daughter nucleus are more stable than the parent nuclei. All right, so that would be the idea. All right, so that will be an overview of what we have been learning and what we are going to learn, okay, in this video. Okay. Okay, so first we need to introduce what do we mean by nuclear fission. Nuclear fission is, in definitions, heavy and unstable nuclei forced to split into lighter nuclei. Okay, so let's see the figure. So see that uranium-235, when you look at the mass number 235, that means that 235 nucleons. Alright, nucleons means proton or neutrons. Okay, and you have a bombarding neutron. So this neutron is going to hit that's uranium. When it is captured by the uranium, then uranium will be split up into two similar size daughter nucleus. Okay, they are beryllium, krypton, but it's just one of the combination. That could be many other different kinds of combination for this daughter nucleus. Okay, so and also they will emit some other neutrons. Okay, so the neutrons emit here most often they will be 2 or 3 extra neutrons. Okay, and this neutron we call fission neutrons, and the neutron used to hit the uranium we call bombarding neutron. All right. Okay, so that's basically the idea. The picture is like this. Okay, a heavier nucleus is split into two lighter or smaller nuclei, right? And plus some neutrons. Sorry. Okay, so here's the equation. All right, you can track that's the all the atomic number and mass numbers are well balanced. All right. Okay. So remember that after any nuclear reaction, including this nuclear fission, the binding energy per nucleon of each daughter nucleus is higher than its parent nucleus. So still remember the idea of binding energy per nucleon. Okay. So that's a very useful measure of how stable a nucleus is. All right, so if you forget that, I might show you the chart, which is here. Okay, so you can see for this chart, right, the vertical axis is what we call average binding energy per nucleon, and the horizontal axis is just the mass number. Okay, so the greater the mass number, the bigger or the heavier the nucleus. Okay, so you see uranium-235 is at the end of the chart. Okay, and is when compared to nucleus like Pb or Pt, platinum, you see is relatively lower in position, right? So as we know, higher the average binding energy per nucleon, the more stable the nucleus is. So when you are at the end of the chart, it tends to climb up the chart to become more stable. Okay, so to become more stable is mass number must be reduced, because the 240 or around 240 is the mass number is the biggest for all the elements available in the chart, and you would like to become somehow around 100 or even so 90, and here the is at the top of the at the highest point of the chart. That means more stable. That's why uranium tends to become smaller. Okay, all right, so that's a very useful chart. So we understand that in a nuclear fission, the binding energy per nucleon of each daughter nucleus, because they become smaller, is higher than its parent nucleus. Therefore, the daughter nuclei are more stable than their parent nucleus. Okay, more stable means they are less likely to be split up. Okay, they less. They have less tendency to become smaller. Okay. Normally, in each fission reaction, there are two similar sized daughter nuclei. We call them fission what? We use this one. We call them fission fragments. Fragments means when you split a heavy nucleus like uranium, you might have different type of daughter nucleus, and these are called what we call fragments. Just like a bomb exploder, there are lots of fragments. Okay, some of them, I mean these daughter nucleus or fragments are very radioactive. Okay, so that means although they don't tend to be split up, but they could still be radioactive to emit some small particles to make them further stable, right? Okay, so and the energy release can be found by the mass defect during the fission by using Einstein equation. Okay, we understand this already, right? Okay, so let's move on to next one. Right? Let's see. Although vast energy can be released through a fission process, it cannot happen spontaneously. Okay, so this word spontaneously means what? Means naturally occur. It cannot occur naturally. Okay, so you can't imagine that a uranium in the nature would just split up. Okay, although we got lots of neutrons flying around in the space, even they pass through that uranium, that doesn't mean the uranium will split up. It's just impossible to happen spontaneously or naturally. Okay, the reason is that not all the neutrons can split up a uranium. It must be certain type of neutron. Okay, it's not, and that type of neutron does not occur in our space. Okay, so that's why there will be some conditions for the fission to occur. To initiate a fission, the heavy nucleus must be bombarded by relatively, okay, what kinds of neutron? Relatively fast or slow. Okay, so people might think, okay, fast will be better because it's more energetic, but actually it's wrong, because when the neutrons are normally very fast, and when they are when they are too fast, too quick, and that uranium can't capture the neutrons. Okay, so neutrons just pass through the uranium without splitting the heavy nucleus. Okay, so to make that fission happen, you need to have a slow neutron. Okay, so that's very important. You understand that? You need to have relatively slow neutrons. Okay, so that's why it's impossible to happen in nature, because in the nature we don't have such slow neutrons. Only a handful of heavy nuclei can capture the neutrons, and also you understand not all heavy nucleus can capture neutrons. For example, we know that uranium, there are several types of isotopes, but not all of them can capture the neutrons. Okay, for example, uranium 239 cannot capture the neutrons. All right. Okay, those nuclei who can capture the neutron we call fission. Okay, we call fission nuclei. All right. Okay, so these are keywords you need to understand. All right. So next we have a very simple multiple choice, just to give you a very quick track whether you understand which one of nuclear reaction is a fission, which one's a fission. Okay, so remember that for fission you need to have a heavy nucleus, rather big nucleus, being bombarded by a neutron and become two similar size but smaller, lighter nuclei. All right, which one satisfies this? Okay, if you can see it, only A satisfy the conditions. For B is a uranium and also neutron, but you see that they form another plutonium, which is a even bigger nucleus, so it's not a fission. For C, you see that first of all, you don't see neutron. Secondly, on the right hand side, there's only one even bigger nucleus. Okay, for D, there are two rather smaller nucleus for a bigger nucleus, because all these are not qualified as a fission. Okay. Okay, let's move on. Okay, so here's some questions about calculation. We all understand that when fission happens, they release energy, and the energy release is related to the mass defect in the nucleus, right? Okay, let's say when a uranium-235 nucleus is bombarded with a single neutron, it fragments into 3 neutrons, cesium-137 and rubidium-96. Okay, so for this, you need to track your periodic table. So I'm not going to do this time because we've done this a few times before, right? So I just write the necessary nuclei for you. Okay, for uranium it should be 235 and it should be 92. Okay, and of course, and that's cesium, which is Cs as symbol, and you have 55, 137, and also you have a rubidium, Ru, it's Rb, and it's 37 and 90. Okay, so you need to check your periodic table. Okay, so periodic table should be in previous notes, or if you use the textbook, you can use it. All right, so you got 3 isotopes, and then you could write the equation. Okay, write the equation of nuclear fission. All right, and okay, so for part A, okay, actually we don't need to calculate the energy release. Okay, so just close this out because I don't think we need to calculate that because we are going to do that in part B. Okay, all right, so let's write the equation. So you got uranium 235 92 is bombarded by a neutron, so that's neutron. Okay, and becomes 2 smaller nuclei. Right. Okay, so you need to balance. You also know that there's some other neutrons. Okay, so how many neutrons do we have here? Okay, so when you add the atomic number, you see that it should be okay. 92 plus 0, 92, 55 plus 37 is 92. So there's no problem with atomic number. So how about the mass number? So mass number 235 plus 1, 236. Okay, 236. Okay, and on the right hand side you got 92, 55. Okay, so we don't know how many neutrons. So let's say that x neutrons, so x times 1. Okay, so you need to solve this. Okay, so, and when you solve this, you see that's x equal to 3. Okay, so you just write 3 here, so that will be it. Okay, so that's the only thing you need to do in the examination. You need to balance the equation. Okay, like I say, what I've said before, sometimes it's 3, but sometimes 2. So you do need to make your own calculation. Don't just memorize the number. Okay. Alright, so let's see boy. Okay, so they give you the mass of neutron, mass of uranium, mass of cesium, mass of rubidium. They are going to ask you to determine the percentage of the original mass, of uranium-235 that was converted into energy. Okay, so we understand that the max defect will be accounted for. That's the energy released. So you need to find the max defects. For mass defect, remember the total mass of reactants should be always greater than the mass of product. Okay, so let's calculate the mass of reactants. Okay, reactants, which is mass of uranium plus mass of neutron. Okay, plus 1 of mass of neutron. Mass of uranium is this number, right? Okay, so let me just copy this. Just easier for me. Alright, not too many digits. Mass of neutron, just like this. Right. Okay, and you possibly just add them. Okay, and for these two, if you add them, you got 2360.005254949. Oh, sorry. 0.52594.9 U. Okay, so mass of reactants, mass of products. So mass of products. Okay, so that would be times 3 times mass of neutrons. We got 3 neutrons. Okay, then you have to use your calculator, of course, and that will give you 235.867.354.25U. Okay, so you see, obviously, mass of reactants is greater than mass of products, so you could find the mass defect. Okay, so the mass defects will be the first number, this number. Okay, take away this number. Okay, and that will give you Okay, and the question is percentage of the original mass converted into energy. So percentage of mass converted based on the mass of uranium. So you need to use this one divided by mass of uranium. Okay, so that means you use this delta M divided by the mass of uranium. Okay, where's the mass of uranium? Here's the mass of uranium. Right, and you have to convert this into percentage. That means you times 100 divided by times 100%. Alright, so it will give you 0.079%. So you see, the percentage wise is very small, but since we only need very small mass to release huge amounts of energy, because that's delta M times C square. Okay, alright, good. And okay, let's look for another one. Okay, so here's another equation. So you need to write the nuclear fission. Okay, so this is another nuclear fission from plutonium. Okay, and then you need to calculate the percentage of the original mass of uranium that is converting to energy. Okay, so you might want to try now. So I'm going to give you some time. You could do it now, and we come back. I give you the answer, right? Okay. Okay, not sure you've done that. Okay, so if you have done that, you can track. Okay. Okay, so here's the answer. So here's the equation. Okay, again, there are 3 neutrons released, and also you need to find the percentage of mass converted. Okay, mass reactant, mass of products, mass difference, and also percentage of mass loss or mass defect. Alright, okay. Okay, so it should be okay. No most difficult calculation. Okay, so then we're going to consider another very famous idea about the nuclear fissions, about the chain reaction. Chain reaction means one reaction followed by the other. Once you started, it just continues without stop, without termination until you exhaust all the radionuclear. So that means chain reaction. Okay, so how nuclear fission could become chain reaction? All right, so let's have a look. You see, for example, if my model only released 2 neutrons, I've said it might be 2, it might be 3, right? So if I got slow neutron to hit on, that's uranium, then you got 2 fission neutrons. And if that's fission neutrons, I could effectively slow down both neutrons, and these 2 can strike another 2 uranium. So one decay of uranium will lead to 2 decays of another 2 decays of uranium, and 2 decays of uranium will lead to 4 decay of uranium. So it's effectively a geometric sequence: 1 uranium, 2 uranium second time, 4 uranium third time, and could be 8 fourth time, right? So this is what we call chain reaction, because you have to keep, because for the reaction there are more neutrons released. So as long as there are neutrons released, these neutrons could hit other uranium. But of course, you know that neutron released are much faster than the initial bombarding neutrons. So you need to find some way to slow these neutrons down before they could strike another uranium, get captured by uranium, and make that fission happens. Right? But anyway, it's just the idea of chain reaction. Right? Okay. So the fission neutron, when slowed down properly, can cause other uranium atoms to undergo fission. This process is called chain reaction. Okay. Okay. The key is you got neutrons and you slow down the neutrons. All right. Okay, each fission process generates vast amounts of heat. This is used to generate electricity in nuclear power plants. So that's why we got a lot of nuclear power plants, because you got chain reaction. That means you don't need to worry about whether you need to add more uranium into the reactors to keep that to keep the reactions going. Actually, once going, you will keep going for a very long time. Okay, but of course you have to change the fuel rod of uranium from time to time, but it's just like possibly in every year you need to change once. You don't need to do it daily, right? Okay, to obtain steady reaction rate, the number of fissionable neutrons produced per reaction should be. Okay, so if you want to have steady reaction rate rather than accelerating reaction rate, okay, if you have accelerating reaction rates, then it's out of control. Then there will be explosion, there will be leakage of radioactive substance to the atmosphere, right? So to keep a steady reaction rate, so you could control the scale of reaction. Then you can't let this happen. You can't get both neutrons, both fission neutrons, to hit another two uranium. You can only do it like, okay, so for every uranium, if I got neutron to hit it, okay, so I got two neutrons. All right, so I'm going to, okay, somehow absorb these neutrons. So only one neutron can be used to hit another uranium. Okay, so this uranium again, if for example two neutrons, okay, then you just try to, okay, absorb one of the two. So every time you absorb the extra neutrons, but you keep at least one neutron available for the next reaction. Okay, so the number of fissionable neutrons produced per reaction should be 1. Okay, right? So what happens if you fail to control that reaction rate? It just become 1 to 2, 2 for 4. Then it's just is the not for the power generation, it's for the atomic bomb. Okay, it's for weapon to do mass killing. So that's very different between the weapon and the civilian use of the nuclear powers. That's part you need to understand, right? Okay, so let's go to see another one, which is what we call nuclear fusion. Okay, so nuclear fusion means exactly the the opposite process, which you will see two lighter nuclei fuse together to form a heavier nucleus. Okay, here's the example. So I got two hydrogen 2. So normally hydrogen is 1, but they got some isotope we call deuterium. So deuterium is hydrogen 2. When two hydrogen 2 they fuse together, they might become a helium and a neutron. So that neutron is not as important as in the fission, because that neutron is just a product which is not going to be further used. But that helium is the one of the products. All right, and the process you will see two lighter nuclei to become a bigger, okay, nucleus. So this is what we call nuclear fusion. And in nuclear fusion, again, the average binding energy per nucleon of the lighter nuclei is, again, it's lower. Okay, average binding energy per nucleon of the lighter nuclei, right? It's lower. So that's why they want to become more stable. They want to form heavy nucleus. Unlike the previous fission one, because for fission one, the heavy nucleus tend to become smaller, so that's the binding energy become higher. But this time, the lighter nuclei, they try to become bigger, so that's the they will have higher binding energy per nucleon. All right. Okay, so we can justify this by looking at the chart here. Okay. Right, so for lighter nuclei, you can see hydrogen 2s over there, so on the other side, on the other end of the chart. So you see it's pretty low. The average binding energy per nucleon is just about 1 unit. Okay, so that's why it would tend to become bigger. If it becomes helium-3, so it becomes from 1 to 2.5, so that's 1.5 times increase in terms of average binding energy per nucleon. So that's why it tends to happen. Okay. All right. So let's go to. Okay. So nuclear fusion can release vast energy, but it cannot happen spontaneous on Earth, just like fission cannot happen spontaneous on Earth, even though they can release vast energy. because there's some energy barrier to stop it from happening. Stop it from happening. Okay, to initiate fusion process, there are two conditions. So first conditions, because you see that nuclei, okay, they are positive. Okay, so if you want them to collide, you want them to fuse together, first of all, they have to overcome the electrostatic repulsion between two positive particles at a very close distance. Okay, so that means that lighter nuclei must travel at an exceptionally high speed. Okay, so how could that happen? That means you must have extremely high temperature in the region of 10 million Kelvin. So 10 million Kelvin is not a temperature we could face in our daily life, right? There must be enough amount of such nuclei to make frequent condition. That's second condition, to make frequent collision per unit time. So you need to have a lot of such lighter nuclei around. Okay, so in what situation you will have a lot of lighter nuclei around? That means you need to contain them into such a small space. So that means it's extremely high pressure. Okay, so that two, simply put, that two conditions: high temperature, high pressure. Okay, so and these conditions are very demanding. So normally on the Earth, for our technology so far, we can't design such a container to withstand such high temperature, high pressure. Okay, right? So, but that will happen within the core of the sun or any stars. Okay, so the energy from the sun or the stars are actually for nuclear fusion, but we can't simulate that on the Earth simply because we need to design a container first, but so far it just hasn't happened. All right, so the next question, a multiple choice, is very simple. Which one's nuclear fusion? Remember the definition of nuclear fusion, where two very small nuclei become a relatively bigger nucleus, all right, and plus some neutrons. Okay, so which one looks like this one? A is a very big nucleus with an neutron, so it's not the case. B is a rather big nucleus, nitrogen with a neutron, so the sizes of two are just has such a huge difference, so they don't like the case as well. So C, hydrogen 2, hydrogen 3, they got similar size, and when you compare to the pole down the right hand side, it becomes a bigger nucleus, which is helium. Okay, so I think C will be the case. Yeah. Okay, so here is another example, just similar example for our so it's similar example for just like the fission one, right? But this time you got two hydrogen isotopes, so hydrogen 2, hydrogen 3, okay, and they need to fuse together to produce an alpha particle. So you know alpha particle helium and a neutron. Okay, write an equation. All right, so I don't think you need to visit that periodic table this time. Okay, all you need to do is to remember hydrogen. Hydrogen must have one atomic number. Okay, and that's hydrogen 2, hydrogen 3, okay, becomes helium, alpha particle, 2, 4. Helium must be 2, 4, okay? And one other neutron, so neutron 0, 1. So can we balance Okay, atomic number 1 plus 1, 2. Okay, and right hand side 2 plus 0, 2. Okay, and mass number 2 plus 3, 4. 2 plus 3, 5. 4 plus 1, 5. Okay, so all things are balanced. So A will be the case, right? How about boy? Let's see. Okay, calculate the energy release by the process and hence percentage of the mass. Okay, so it would be the very similar question than before. Okay, so I might give you some time, try to do it. Okay. Okay, so that will be the answers, right? Okay, so you need to find the mass of reactants of hydrogen 2 and hydrogen 3, and also you need to find the mass of the products, all right? And you need to check whether the mass of reactants is greater than mass of products. It should be the case, otherwise it won't happen. Okay, so and after you get that's delta M, and so that's the max defect. Okay, and use that delta M divided by the total mass of reactants, so you got the percentage. All right. Okay, so this would be another example we need to try by ourselves. Okay, so the answer will be in notes. All right, so you can track the answer from the notes. Okay, and so here. Okay, so and we got fission and fusions. So we need to compare the energy release. So first of all, you see fission and fusion, they comes from two opposite ends of the chart. Okay, so for fission, it comes from the end of large mass number. That means the heaviest nucleus. All right, so it becomes smaller by doing fission. So when it becomes smaller, you go to the middle part of the chart. Okay, in the middle part of the chart, the average binding per nucleus becomes higher. That means it becomes stabler. Okay, and for the fusion part, it does the same, but from the other end. Okay, it goes from like very small average binding energy per nucleon to relatively greater, okay, binding energy per nucleon. So that means it becomes more stable. Okay, so both are actually they have one purpose, to get their binding energy per nucleon bigger, right? Okay, so that means both of the reaction will release energy. Okay, but when you compare the fusion part, you see a much steeper rise. For the fusion part, I mean this part, you see a steeper rise. Okay, in terms of the average binding average binding energy per nucleon. So you see it rises so rapidly. Okay, so that means for every unit change in nucleon number, okay, so the energy release will be much higher. Okay, on the other hand, you see for the fission, is still climbing up, but it's just the slope is much smaller. So that means the change in energy is not that significant per nucleon speaking. All right. Okay, so that's why we have a observation, and you need to conclude that the fusion part of growth. The fusion part of the graph shows a much steeper rise than the fission part. Okay, fusion releases greater energy per unit mass. Okay, so that's why the sun is much effective. It's much effective in terms of releasing energy than our nuclear power plants, because our nuclear power plants is using fission and the sun is using fusion. So it's much efficient energy generation by using fusion rather than fission. Okay. Okay, theoretically, both fusion and fission will stop at the highest point of the graph, which is liquid. But since the demanding energy barrier for the initiation of the both process, they stop well before reaching the peak. All right. So, for example, okay, for the sun, most of the reactions stop at helium-3. Okay, for our nuclear plants, most of our reactions stop around like SN or XE. Okay, it's very hard to go closer to the liquid, to the highest point, right? Okay, and in my notes I give you some extra reading, okay, about pros and cons, or about the nuclear power plants. Okay, so because I know for the assessment, the investigation project, some questions are related to nuclear power generation. So I think it will be better for you to understand more, to have more information about the nuclear power plants. So there are some very common advantages and disadvantages regarding nuclear power plant. All right. Okay, you just need to read that by yourself. I'm not going to read that for you one by one. Okay, and also there's an advantage of using fusion over fission, but of course we understand there's obvious advantages of using fusion over fission, but the problem is there's technological barrier that's we currently we haven't succeeded in using fusion to replace our fission power plant. Okay, all right. So that's just for your extra reading. Hopefully, it will help your assignment. All right. Okay. So okay, you might try some practical questions over here. There's some practical questions. Okay, and also you might see we got answers as well from the textbook. Okay, all the answers from the textbook. All right. Okay, so hopefully you could understand this chapter better after the video. All right. Okay, so if you have any problem, any question, please email me, or you can write something in the collaboration space in OneNote. All right. Okay, so see you next time. Bye bye.